We are project creators from Birla Institute of Technology and Science, Pilani, KK Birla Goa campus. This is our second time participating in the University Rover Challenge. Given the testing times that COVID has brought along, the team is working diligently to bring this year's rover to life. Improving upon our first team organization, Project Kratos, this year is now divided into 7 subdivisions: Mechanical, Controls and Electronics, Power and Modularity Division, Autonomous, Communications, Life Detection Subsystem, and Data and Logistics team.
The mechanical subsystem designs and manufactures the framework of the rover, the robotic arm, and the hardware for the life detection subsystem. Learning from our mistakes in the previous design, we have completely revamped the mechanical design of the rover. The box-shaped chassis will be made of aluminum sections and has a removable electronics box for easy storing, accessibility, and servicing of the electronic components on board. A modified double lambda rocker bogey mechanism along with a differential bar averaging is used. This year, the suspension is more robust, keeping almost similar weight to the previous version. The averaging has also been pushed to the rear of the rover to increase the stability of the rover. We are using a 6-wheel differential drive mechanism. The wheel assembly has been redesigned to ensure easy assembly and protection to the drive motors. We have redesigned our 3D printed flexible wheels to be more light while providing the required shock absorbance. The threads are incorporated directly into the wheels to increase the traction. The high torque DC gear motors enable the rover to easily climb slopes up to 50 degrees. Our 5 degree of freedom robotic arm has 2 linear actuators. The arm now uses carbon fiber tubes extensively, making it lightweight yet preserving strength. The base rotation has been redesigned with spur gear drive to increase robustness. The end effector is a 4-bar linkage gripper which uses a differential bevel gear mechanism for the pitching and rolling motion. It can carry loads up to 7 kg and also perform high precision tasks.
Our inverse kinematics based controller on ROS allows the operator to easily manipulate the end effector position in space. This is augmented with a closed-loop feedback system from the linear actuators to meet the high precision requirements.
Last year, the autonomous subsystem completed a dynamic path planner test run on Gazebo. Since then, we have improved our efficiency using methods such as Octomap along with custom scripts to map obstacles more accurately onto a 3D occupancy grid. To test how the system would perform during on-site tasks, we chose the gaming engine Unity. Using the ROS Pitch library, we simulated an off-board system with an environment, camera, and GPS sensors just like the actual task.
The system is also able to detect AR tags from a distance of roughly 10 meters and track them accurately. We have also completed training a custom YOLO-based network which we plan to use to detect poles. The team is currently working on integrating the detection and path planning parts of the system to run together.
Improving upon our control system, this year we are using STM32 over Arduino as our microcontroller. Our drive controller in manual mode allows the rover to be teleoperated using a joystick, whereas in autonomous mode, the rover follows the waypoints generated by the dynamic planner by computing rover velocities using the PID algorithm. This controller uses a fusion of GPS and visual inertial odometry data as feedback. The computed rover velocities are passed to STM32 over ROS serial, which computes the wheel velocities using differential drive inverse kinematics and sends them to the motor drivers over UART.
For powering all onboard components of the rover, 2 lithium polymer batteries are used with specifications decided after battery drain test. Modular power distribution boards and PCBs are designed for easy access and quick replacement of components. For ensuring safety of the rover, an emergency stop button is installed and an adjustable current capping mechanism is implemented. Further, a battery management system is designed to regularly monitor voltage and current parameters, predict charge left in the battery, balance voltage of cells, monitor its temperature, and to estimate the state of health.
For communication between the rover and the base station, we are using rocket M2 radios with an omnidirectional antenna on the rover and a sector antenna on the base station that gives a coverage area of 120 degrees. We are employing a video compression algorithm that enables us to launch multiple camera feeds from the onboard camera simultaneously with very less latency.
The life detection subsystem focuses on classifying soil and rock samples into extinct, extant, or no life. Rock analysis is performed using the Image Processing Unit or IPU. We use an ensemble CNN model and image processing techniques to identify and classify rocks. We use specific green and red LEDs to highlight any living colonies inside or under the rocks. For the soil analysis, we first do a soil organic content estimation by capturing accurate soil color using the IPU and matching it with a soil Munsell chart. We also perform various habitability estimations using atmospheric sensors and soil images. Finally, we have qualitative colorimetric tests and a custom UV spectrometer for identifying specific biomolecules. For this, we have a ratchet wheel soil collection mechanism, filtration and distribution system which is contamination resistant and follows the strict no spill policy. We have engineered a controller to actuate the stepper motors and DC motors in the soil collection mechanism. The STM32 microcontroller actuates the setup as per the joystick commands sent via a ROS topic.
We are currently working on making our rover robust and modular. This has all been possible due to the hard work of our team and support of our seniors and professors. We hope to see you in URC 2021.